Hey guys, so as discussed in the last class, we are going to continue our discussion on the energy band diagrams of the PN junction. So I think last lecture it's very understood for you guys. So the white color which is normal, so there is no difference. That will be the band difference that will happen. The red color which is the forward bias, that will be forward happening, and blue is the reverse bias. So only the thing is that the depletion region we are converted that with the energy band diagram. So both things are same. So there is a correlation between the depletion region and the energy band diagram of the PN junction. So that only we are fine. So today we are going to find the V0, the built-in potential that is got developed. So we know that Q V0, which will be termed in EV. So this is energy level. So from this, how can we find out the voltage, built-in voltage potential? Let's see. So we know that Q V0, which will be the summation of the first energy level gap and second energy level gap, that is EFN and EFI, EFI and EFP. We already know how to find out these difference, that in the energy band structure itself we have discussed. Okay, so let's bring that together. So if we substitute the formula of EFN minus EFI, then the formula it will be KT ln NA NN divided by NI square, NI normal NI. So KT ln NN divided by NI, NN or even ND, that is anything fine. So then KT ln PP divided by NI. Okay, so let's combine both things. So let's take KT common outside and then let's bring it this together. So Q V0. So if we take KT, or if ln A plus ln B can be multiplied together, so that is NN NP PP divided by NI square. So this is the formula that I said in the last class also. So this is how we can derive the formula from this one. So this one can also be approximately written as KT ln NA ND divided by NI square. Okay, so I hope it is understood. So even we can, here the two charge carriers is dependent, so both the acceptor and donor atom. So if it is purely an n-type or p-type semiconductor, then how we can find out this thing? So here Q0 is there, Q is there, right? So if we divide by Q, then we can directly get V0. V0 is equal to KT by Q. So KT by Q can also be written as VT. So ln NA ND divided by NI square. So I hope you guys now able to differentiate about KT by Q. So KT by Q can be written as VT. So ln NA ND divided by NI square. Okay, so this is fine, right? So now what we can do is that now we can divide this term. So let's take this term. So let's, if we have to make it particular to one type, then we can return this as a KT by Q ln. Let's divide the minority charge carrier. So PP NI square divided by NN. So which can be also written as VT ln PP divided by Pn. So here you can clearly see that it is an p-type semiconductor. So which is an this is an p-type charge carrier, where we have taken a p-type charge carrier which is majority in the p region and the minority charge carrier in n region. So we have combined both the charges from the same PN junction. So similarly we can also write for Vt. So Vt which will be ln Nn divided by Np. Okay, so these two formulas also can be derived. So the total of three formulas, which is 1, this is 2 and this is 3. Okay, so based upon your question we can use any kind of formulas that we are needed in the thing. So the thing is that, so this is what this will give some amount of V0, right? So this will be the voltage that is needed to be externally triggered. So if the Vf or Vr which is greater than this, then we can use any kind of if for an example, if we are applying Vf, so Vf is the thing, Vf is greater than V0, then we can consider there will be current movement and the potential barrier will be reduced to further. If Vr, which is what we say, which will be less than V0, or even not a V0, if we add Vr, then the depletion region will be definitely increasing. If Vf is less than V0, then there will be depletion region will be there, but current density will be here only high. So scenario 1 and scenario 2. So comparing one, the scenario I current will be more than scenario 2. So that is what the thing here. So that we have to understand. So based upon the V naught, that will be based upon the material, there will be some kind of inbuilt voltage that will be developed. From that we have to apply the enough amount of external voltage in order to get our required current or required application. Okay, so I hope it is understood for you guys. So from here we have completed our analysis on the forward bias, reverse bias, everything. So next we are going to start a new topic on types of junction. So let's start the thing like different types of junction. Different types of junction. So based upon the doping profile, there will be different types of junction will happen. So one thing first is the abrupt. There will be step junction or uniform junction or anything. So we will state that as a abrupt junction. So abrupt junction, or even we can state this as a uniform doped profile will have this one. So uniform junction. The second thing is that linear junction or non-uniform junction means the doping profile will not be will not be uniform. Sorry, non-uniform. So based upon the profile change, like doping profile changes, the observation of electrical field, voltage, everything will vary. So first let's start with our first type of junction, that is uniformly doped profiles. So uniform junction. Okay. So the uniform junction means this resembles the charge carriers. So this is purely on charge carrier dependency. So I will plot the charge carrier diagram for you guys. So here if you see, so this is reference. So this will be the charge carrier. So if you take an example, this will be P side and this will be N side. So this is Na and this will be Nd. So we are drawn only majority charge carriers Nd and Na. This is x is equal to 0 and which is x. This axis is x. And this is charge carrier concentration. Okay, so this is how. So if the profile is based upon the profile, there will be variation. So that is not our interest. So this is how. Here you see the uniform, the doping of the material which is uniform throughout the semiconductor. So that's the thing. So let's draw the charge carrier diagram for this, charge density diagram for this one. So if we draw the charge density diagram, then how the thing will go is that it will trace the boundary. So let's consider some region as a depletion region and then let's trace its boundary. So let me draw one depletion region here. So let's take this as a depletion region. So this is the depletion region. So let me dictate this line. Okay. So this is what the region. So if we draw the charge carrier concentration here, so let me take a blue color. So here there will be no charge carrier variation. So it will be traces its boundary as it is. So it will be tracing its boundary as it is. Then here we know that is negative. So the charge carrier here will be like this and here it will be positive. So in order to indicate this negative acceptor atom, so we will trace the boundary to negative region. So that is why we will be tracing that to negative region. So we will trace that to negative and then this charge carrier to positive. And then again trace back to boundary. Okay. So this one we represent as minus 0, sorry, the acceptor atom and here the donor atom. So this is minus xp and this is xn. This is this height. This height we will be representing that is qnd. This height we will represent as minus qna. Okay. So if we consider the charge profile, the rho v, so rho v which will be equal to minus q na in p type region, in p region, and rho v at n type will be q nd in n region. Okay. So if we combine both the thing, so let's combine both the qd which is equal to qd because it is a charge neutrality condition. So if we combine the system, the charge neutrality, then qnd over the area into xn which will be equal to qna over the area xp. Okay, I hope it is understood. This xn and the area which is taken from the length. So we are just calculating the area of this region. Okay. So if we cancel all the things, then the remaining thing will be nd xn which will be equal to na xp. So which is one very important relation. We will be relating that further. Okay. So I hope we could able to understand the charge neutrality, like how from the charge neutrality equation we able to get another one definition. So if they give doping profiles and the distance of xn, then we can directly calculate the value of xp. So depletion region width can be calculated from this one. So from this we have to extend our understanding to the electrical field and voltage things. So far we have identified the charge neutrality condition from here. So in the next class we will be further extending this to electrical field. So I will be teaching that, continuing the discussion from the next class. So stay tuned guys. So let's start the discussion from next class. So I hope it is understood for you guys. If you guys feel any difficulties, please ping in the comment section. Thank you.